All right, welcome back. This is for Math 140. This is the final preview or review, however you choose to see it. So the question that was asked was number 4 on part 2. This has to do with the composition of f composed of g and g composed of f of x, where g of x is equal to the cube root of x minus 5 and g of x is equal to x cubed plus 1. So the question asks, are g composed of f and f composed of g, given these are, I guess we use r twice, are f and g inverses? So it asks us to show that they are or are not, and then explain why. So the inverse, f composed of g of x, if f and g are inverses, this should give us back the identity function, which is x, which also means that g composed of f of x should also give us back the identity function. So it's a requirement for f and g to be inverses that the composition of the two functions should give us back the identity function. And a way to think about that is multiplying and dividing by the same number should give us back the same result, right? They should equal, they should undo and do each other. So addition speaking, like if I have x plus 1 and I subtract 1 from it, that gives us x. Likewise, then if I have x minus 1 and I add 1 to it, those two operations of addition and subtraction undo each other, and those both give us back the identity function. Okay, so those would be inverses, additive inverses of each other. So now we're seeing if they're functional inverses of each other, and that's going to give us then whether or not the result is if f and g are inverses. Okay, so let's try to ground this in something that you are familiar with. So let's compose the two functions and see what we get. And if we get that each direction gives us x, then they are inverses. So f composed of g of x going this direction means that everywhere in f I see an x, I'm replacing it with g of x. And I'm going to rewrite f with a little bit different notation here. I'm going to write this as x minus 5 to the 1/3 power, where the root, or the index here, becomes the denominator of the fractional exponent. Okay, and so I'm going to replace everywhere in f I see an x, I'm going to replace it with f of x here. Sorry, g of x. So I have x, which is going to be replaced by x cubed plus 1 minus 5. I'm going to raise that to the 1/3 power. Okay, and simplifying this out, I get that this is x cubed minus 4 to the 1/3 power. And now you'll notice that this is not equal to x, and it doesn't simplify to x. So at this point, we can say that f and g are not inverses of each other for the fact that this does not simplify to x. So if it fails either direction, then they are clearly not inverses of each other. But let's just go ahead and compose g composed of f of x and see what that gives us. So g composed of f of x. So in this case, everywhere in g I see an f, or I see an x, I'm going to replace it with f. So I have, in this case, I'm going to cube that and plus 1 to it, and so that's the x term here, and I'm going to replace it with the square, or the cube root of x minus 5. Okay, and so here, the cube root and the cube, those are going to undo each other, and so we're going to be left with x minus 5 plus 1, which gives me x minus 4. So again, that's not equal to x. So in both conditions, neither one of them are equal to x, and so that is clearly not inverse functions of each other. Okay? All right, so I hope that was helpful in relating this idea, and now we're going to jump to the next problem. All right, welcome back. In problem 6, we're looking for the asymptotes of all kinds for this function f of x. So the question is asking for vertical asymptotes, horizontal asymptotes, and if there are any slant asymptotes. So we can consider these. We'll kind of go in this direction in terms of ease of computation. So for slant asymptotes, the degree of the numerator has to be greater than the degree of the denominator. And typically, it has to be exactly 1 usually exactly 1 degree greater. So for example, x squared plus 1 over x plus 2, the degree here is 1 more than the degree downstairs, and so this may have a slant asymptote. Okay, but in our function, since the degree of both terms are equal, we do not have a slant asymptote. Okay, so there are no slant asymptotes, which allows us then to move over to the horizontal asymptotes. And so for horizontal asymptotes, okay, we want to look at what happens when x gets really, really big. So in other words, when x goes to positive infinity, and when x gets very, very small, so when x goes to negative infinity. In other words, we're just thinking of really big numbers as we go. If you think about the, this is the x and the y-axis here. So the x-axis here. So as we go out really, 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 really far in the x direction and really, really, really far in the y direction, or no, sorry, the negative x direction, we're trying to see what the function's doing, okay? And so for a rational function, the largest degree of top and bottom of the numerator and the denominator here are really what's going to matter. So when x gets really, really large, like out here at like 20 million, right? The 20 million squared is going to be much bigger than just 20 million, because this is 20 million times 20 million, and that's the degree of the top and the bottom happen to be the same. So so let's consider that. So when x gets really large, we get f of x. As x goes to infinity, we are left with 4 of x squared over x squared. So you can kind of see these numbers are gonna kind of cancel out, right? And so it looks like as x gets really, really large, we're gonna get the y value. That's a 4, not a y. We're gonna get a y value of -4. So it looks like it's gonna try to tend to the value of -4, y equals -4, as x gets really, really large. And in fact, actually, it turns out that for f of x, approximately when x is really, really small, so as x goes to negative infinity, we still have the same situation. We have -4x squared over positive x squared. So when you're thinking about really large negative numbers, because of the square, they're both going to be positive, and so those still reduce to 1, and it looks like, again, it's going to head to -4. So in both situations, then, it looks like we have a horizontal asymptote at y equals -4 for both the negative and the positive directions. So whatever the function's doing, we definitely know that when we start really, really, really early, or we go really, really, really late, really, really, really late, really, really, really early, the value of the function tends to -4. All right, so let's jump into the horizontal asymptotes then. And so this only occurs when the denominator is equal to 0. So the numerator is just going to chill in this problem. We don't really have much of an effect, other than is it the case if we have a removable discontinuity there, okay? So I'll factor both, but really it's the denominator that's going to play a role here. So f of x is -4x squared plus 1 over x squared plus x minus 2, okay? So in this case, this is a difference of squares. I can rewrite this as 1 minus 4x squared. And then this down here, this isn't a difference of squares, but it is factorable. So, so this is a difference of squares. So remember, a difference of squares, you have a squared minus b squared. Well, that's going to give you a minus b times a plus b. And so if we recognize a as 1 and b as 2x, then this factors very nicely. And so the bottom part here, we can use our schema here of 1. So a times c is going to give me -2, and my b term is a positive 1. Since 2 is prime, the only two numbers that multiply to 2 are 2 and 1. And I need it to be a positive 1, but one of them has to be negative because I have a product that's negative. and so this bottom one will factor with these factors here. Okay, so factoring everything together, then we have 1 minus 2x and 1 plus 2x over, let's see here, we have x minus, well, x plus 2, and then x minus 1. If I divide by a here, in both cases, a is 1, so it's not going to affect the factored value. And notice that these factors, there's no factors that cancel out, so it looks like I have two vertical asymptotes, setting each of these equal to 0 individually. I get x plus 2 equals 0, and I have x minus 1 equals 0. Subtracting 2 from both sides, I get x is equal to negative 2, and adding 1 to both sides, I get x is equal to 1. Okay, but again, these are the vertical asymptotes, so I don't want x to equal 0, so I don't want x to equal either of these two values. Okay, so my vertical asymptotes occur when x is equal to negative 2 and when x is equal to 1. I have a horizontal asymptote when y is equal to negative 4, and I do not have any slant asymptotes. Okay, hope that was helpful, and now we're going to jump to the next problem. Okay, welcome back to this problem. This is going to be problem 8 from part 2. So this is the introduction to vectors. So u is a vector with coordinates negative 2, 5, and v is a vector with coordinates negative 1 and negative 8. So just as a picture to kind of have in our heads, these are, you can literally think of these as like ordered pairs, but the result is a vector. So we're going to come over here at negative 2 and positive 5. Okay, so there is our first vector. This is u. And then our second vector is at negative 1, positive, no, negative 8. Negative 8, yeah, and so that's going to be down here in the third quadrant. So try to make it a little bit, well, it's not perfect, but this would be negative 8 here, and that's negative 1. Okay, so you can see that this vector is down here in the third quadrant, and that's our v vector, and then our first vector, u, is in the second quadrant there. So these are the vectors that we're looking at. And now part A wants us to find the magnitude and direction of u. So this is no different than finding the corresponding reference angle, theta prime, and then we actually want this angle from the positive x-axis. So that's the actual directional angle, but we need, in order to find that, we need to find the fact that it's in the second quadrant. And likewise, so we're going to use our right angle trig results here to figure out those corresponding angles. So I know that tangent of the angle theta is equal to opposite over adjacent, and I'm ignoring the negative, if you will. I'm putting it in like absolute values because the reference angle is going to be in the first quadrant, and then I'll use the difference from pi to that angle to find the actual value of that angle. So tangent of theta is equal to 5 over 2, and so the theta value is going to equal arctangent, or tangent inverse, of 5/2. And let me see what that value is. So plugging this into the calculator, I get that it's approximately equal to 1.19, this is in radians, which is approximately 68, let's say 2 degrees. Okay, so that's an approximate. So that's the reference angle. Okay, so to figure out the actual angle there, I need to subtract this would be theta prime, really. So theta is going to equal pi minus that 1.19, which is approximately equal to this is 1.95 radians, which is also approximately equal to 111.8 degrees. Okay, so that's for u, and that's the direction, and then the magnitude. The magnitude is just it's literally just the. So you can think of this as the Pythagorean theorem, right? You know the x-coordinate, you know the y-coordinate, so these are the legs of the right triangle, and so we just need to use those to find out the magnitude. So the magnitude of u is equal to the square root of a squared, negative 2 squared, plus b squared, 5 squared. And so this is going to equal 4 plus 25, which is going to equal the square root of 29. Okay, and we'll leave that as an exact answer. We prefer that to the not exact answer. Okay, now looking at the magnitude and direction of v here, we're going to do the exact same thing, but now the v is in the third quadrant. So the only difference between these two calculations is here theta is going to add pi to this. So this will be the only difference in the line. Everything else is exactly the same. So tangent of this theta prime, which would be this angle here, that's the theta prime for v, is going to be equal to the coordinate opposite, negative 8 over negative 1 in absolute values. It turns out to be positive in this case, which is okay. So this is just going to be, so we're looking at theta prime is going to equal arc tangent of 8, which I think that is 1.44 radians. So we're going to add that then to pi. So theta is going to equal pi plus 1.44 rads, which gives us an approximate value of 4.59, let's say 4.59 radians, okay, which is, I can convert that to which is 262, which is approximately equal to 262 points, let's call it 9 degrees. Okay, all right, and then so that's the direction. This part right here is the direction, and then the magnitude of v. Okay, that's going to equal again the a side plus the b side squared. Okay, so it's going to be 1 plus 64, which is going to equal the square root of 65. Okay, so that's the magnitude of v. And now for the dot product of u dot v, so I'm going to move that part down here. So u dot v, so the dot product is just the multiplication component-wise of each vector and then adding the corresponding values together. So so we're going to have negative 2 times negative 1. I'm multiplying the first component, and then I'm going to add to that the product of the second component, so 5 times negative 8. So this is going to give me negative 2 times negative 1 is a positive 2. This is going to be plus a negative 40. So the corresponding dot product then is a negative 38. And that takes care of each of the 3 parts for this problem. And that concludes all of the part 2 problems. I'm going to jump back in and re-explain problem 21 from part 1, which I think I made more unclear in class. All right, welcome back. So in this problem, it wanted us to identify, so the standard form of f of x is a sine bx plus minus c plus d. And so what we saw in class is, and you had an exploration with this in GeoGebra, that the d term moves the function up and down. So this is a vertical shift, and so it moves it up with the same sign, okay, or down with the same sign. The c term, this is the phase shift, and so what does that mean? Just like the vertical shift with d, phase shift means it's going to move the function left or right. This is always the same sign as d. Okay, and c is the phase shift is always opposite the sign of c. So if c is positive in here, then it's a shift to the left, and if c is negative, then it's a shift to the right. Has to do with the pesky minus sign there. And then b here, okay, what is b? This is the frequency of the wave, and so this is how often the waves are going past you. If you imagine you are standing on the sea and you're watching the waves go by, and you start your clock here, and then you count. Okay, so there's one wave, and then this wave is next, right? So then if you come down in time, and so now here 2 is, and here's 1. Okay, so a little bit of time later, this wave now is here, and so it's how fast these waves are going past you. So here's the third wave, and a little bit of more time later. And if I was better at trying my thing, so here's 1, 2, 3. So imagine these are actually the same waves over and over again. So what I'm trying to show here is that you're standing still and you're just counting how many waves have come past you over time. How fast they're going past you is the frequency. Okay, so that's what that is. And so its relationship, the period, which is the distance between each of these. So this is the period. Often, I don't know why it's written as capital T, but this is the period. And so it's the distance. The period is the distance between these two, and the frequency is how fast those things are going by you, is equal to 2 pi over b, if we use b as the frequency notation here. Okay, and so that is one of the areas I think that I was a little bit confusing about what we were exploring in class today, and connecting to. So, and then last but not least, of course, is the amplitude. So A is the amplitude. And so if I was going to draw a wave like this, then in the middle, if you can imagine kind of like dividing the highest point and the lowest point in our wave here, the vertical distance, either here or here, the total vertical distance from the highest point to the lowest point is 2a, and so that means that each of these individual locations are the amplitude a. And the sine of a, like what we saw, because our sine of a is negative, what that means is it just inverts when the wave is above and when it's below. So negative a would be down here and up here. So this would be when negative a. So it doesn't change the height of the amplitude. All it changes is when the maximum and minimums are occurring at. Okay, so the amplitude of this wave is 3. The location of where the max and mins occur happen to be relative to where the sine is. Okay, so let's putting all of this information together. We identify d as equal to +1, which shifts the graph up 1. Okay, so it's moving the whole graph up 1. We recognize c is the phase shift, and that's equal to, we have a positive pi here, so that's going to be a negative pi. Okay, so what does that mean? It means it's shifting the graph. So it's shifting it with a negative pi. So it's shifting it to the right. So how do I draw that? Not how, but where, really. So if this is our original graph, okay, if I have a phase shift of negative pi, it's shifting it to the left. I think I said to the right, but I meant to the left. So it's shifting this. So this graph here, okay, it's like picking this up and moving it that way. And how you might be asking, well, isn't that moving it to the right? I'm moving my coordinate system to the right, but the graph itself is moving to the left. Does that make sense? So I'm moving my new graph, or another way of saying it is picking this graph up and moving it so I'm moving this point to here, equivalently. So so if this is the same graph, then I would have, okay, and so I've shifted this amount to the left. So moving my coordinate axis to this new point is the same as shifting the graph to the left. So hopefully that doesn't make it more confusing, but this is like shifting left by pi units. Okay, so that's what C does, and then let's see, what do we have? B. B is equal to, I think it was 2 in our situation, right? So so if the period t is equal to 2 pi over b, then that's going to be 2 pi over 2, okay, which is going to be pi. Okay, so then the b term is going to have a 1 over pi frequency, meaning that the increase of waves coming through is going to be twice as much because I'm cutting them in half. Okay, so this, make it a full. Okay, so this is 2 pi for the period when b is 1. Okay, but now making it pi, that means that in order to have the same 2 pi distance, what I need to have is hopefully you can see that. Kind of wish I had a different color. Maybe if I can outline it here in blue a little bit. So in order to have the same distance of 2 pi, what I'm going to have is twice as many waves coming through. So they're coming through twice as fast, and that's what having the b term of 2 does. Is it makes a frequency, it doubles the frequency. Okay. Or another way of saying that is it reduces the period by 2. Okay, it cuts the period in half, thereby doubling the frequency. Okay, and then last, amplitude is 3, which means, which shifts negative. The amplitude is positive 3, but the sign changes occurrence, or I should say location, of max and mins. Okay, in other words, if my max is a min, so this is a max, this is a min, this is with positive 3, so a negative 3 would shift, so this is negative 3, so it just switches the direction for those. So that's what the negative 3 does in our original function. Okay, all right, so hopefully that clears up some of the misconceptions or some of the areas of being a little less clear. Okay, and I think most of it would happen to do with the frequency thing. So it's a doubling and halving situation, right? So if you double the period, right, then you conversely you reduce the frequency by half. But if you double the frequency, then you're cutting the period in half. Okay, so if you double the frequency, you're shrinking those waves together, which is why on the graph we saw the waves go from being out here like this. We saw them when we plug in b going to 2, they became this. Okay, so it shrinks the frequency because the period has been reduced. Okay, all right, I hope that was helpful, and I wish you all the best of luck on the final. If you have any questions, please feel free to reach out. All right, have a good one. Take care of yourself, and take care of someone you love.